Good morning to all. I welcome all participants, speakers to second day of our webinar. Today we have two sessions, each of 1 hour. First session will be delivered by Professor Ajit Mohan Srivastav sir from IOP Bhubaneswar. And the second talk will start at 12 to 12:15. That will be taken by Professor P.S. Anil Kumar from IIC Bangalore. I request Devakant sir, scientist from IOP and coordinator for the program, to chair the sessions for today.
Thank you, madam. Welcome everyone and very good morning to all of you. So it is really my pleasure to introduce the speaker who is actually a senior colleague and a distinguished scientist at IOP. So we know very well each other, but on this platform, I have the pleasure to introduce him. Anyway, so Professor Srivastav, just to students or who do not know about Professor Srivastav, he is well known across the country. Professor Srivastav got his PhD in theoretical high energy physics from USA way back in 89. Then he was a research associate at one of the very good place, Institute for Theoretical Physics, University of California, Santa Barbara. Then he joined as a faculty at Institute of Physics in 1994. And his research interest is very on various aspects. Though he is a theoretician, I mean his research interest mostly focus on quark-gluon plasma and this relativistic heavy ion collision, this astrophysics, gravitational wave, cosmology. And not only that, he does this only theoretical research. That is a very good thing I find in him, that he also does experiment related to liquid crystal experiments. And his fundamental understanding on various, he's not only limited to his research area. What I find after interacting with him 4 years of my stay, or 4.5 years of my stay at IOP, so his research interest is not only focused to this one. He can discuss, or he can advise you on various topics as well. Even I have many times I have asked him condensed matter problems, so he can do that. That's what I like in him this thing very much. And he is basically now he will be talking us about today's talk. That is, I think it will be very much important to all the students. It is a very fundamental talk, the universe and elementary particle physics. I think with this short note, I would request now Professor Srivastav to kindly deliver the talk. Thank you very much, Professor Srivastav.
I'll share my full, let's see. So you can see my full screen now?
Yes.
Okay. So thank you, Devkan, for a very beautiful, sweet introduction, and very grateful to you and Professor Ojha for inviting me to present this talk. A very beautiful program you people have arranged, and it will be very useful to everybody participant in this, including me. I learned a lot from Professor Yusuf's talk yesterday. I look forward to other talks also. So my topic is the universe and elementary particle physics. And people who may not know about this joint area may wonder, am I giving two talks or what? Because the elementary particles are fundamental constituents of matter. The upper limit of size is 10 to the 18 centimeters. They might very well be having zero size elementary particles, structureless, but we don't know. We can only put experimental limits, and this is the limit which comes from Large Hadron Collider. If they have any size, it has to be smaller than that. And the area of elementary particle physics deals with understanding properties of elementary particles and their interactions, the most fundamental constituents of matter. It requires techniques of relativistic quantum field theory, which is quantum physics for relativistic particles. This is not surprising because remember, microstructure of matter, we know when quantum mechanics is relevant. You always learn quantum mechanics is relevant when you go to microstructure, atoms, electrons, and all those things. That's what we learn. Of course, then later you also learn in condensed matter system, there are big systems like superconductor, superfluid, at very low temperature, which require quantum mechanics treatment. You don't expect quantum mechanics to be relevant in this regime, which is astrophysics and cosmology. It deals with the structure of the universe, consisting of galaxies, clusters of galaxies, superclusters, massive scale, huge objects, and not at small temperatures, at very, very high temperatures sometimes. Size of the observed universe is 90 billion light years. Light year, light is the distance light travels in 1 year. So 90 billion light years. It's about 10 per 24 kilometers, something like that. So study of how the universe began, how it evolved, how this structure, galaxies, clusters, etc. form. That's the area of astrophysics cosmology. Theoretical framework in this is Einstein's general theory of relativity, which is the modern theory of gravity. Now, in last several decades, these two areas seem as wide apart as you could possibly imagine, but in last several decades, one has learned a very remarkable thing, that these two areas are intimately interconnected. And evolution of this very large universe and its structure cannot be understood until we understand the properties of elementary particles and their interactions. This is the area called as astroparticle physics. Astroparticle physics focuses on how these two areas are deeply interconnected. Now, one may wonder, why does one need quantum physics to understand the universe filled with galaxies and clusters of galaxies, huge objects like that? And the reason for this surprising interconnection lies in the hot Big Bang theory of the universe. The universe was very hot and dense initially, filled with the plasma of elementary particles. It expanded and cooled. And we'll discuss how this interconnection arises, where quantum physics in the universe decides everything about the universe, basically. So first, we'll start having a look at the universe, overall universe. Then we'll get into it, how it evolved and all that. So, I mean, I have given a picture of a galaxy, which is M83 galaxy. It is very similar to our galaxy. We cannot photograph our own galaxy, Milky Way, but this galaxy is very similar. Both are spiral galaxies and about 100 billion stars. If it was our galaxy, the location of our solar system in Milky Way would be somewhere here. This arrow is marked a red arrow. In the spiral arm, not in the center. And if people, I always point out, if anybody is disappointed why we are not a center, everybody wants to be center of stage. You can see hot thing here, and you don't want to be anywhere near there. You know, the Nobel Prize of this year has been given for discovering, for the evidence, providing evidence there is a supermassive black hole, about 4 million solar masses black hole in our center of our galaxy. If you are there, life cannot develop. So we are happy in being spiral arms. So size of a galaxy is about 100,000 light years. That's a distance scale here, 100,000 light years. Now you go further away, talk to million light years length scale, and you see this. This looks like a sort of sky with stars, with some fuzzy object. Nothing is star here. Everything is a galaxy here. So I'm trying to give you the idea how big our universe is. And this is these are all galaxies. It's a cluster of galaxies. Go further away, the distance scale has been marked here, 10 million light years. And this is, this is a Virgo supercluster. These are our local supercluster. It consists of clusters of galaxies. I showed you earlier a cluster of galaxies. This is clusters of galaxies. So these are, every dot here is a galaxy by itself. Remember, every galaxy has 100 billion stars, like our sun or bigger. And this is, every dot is a galaxy by itself. You go further away, 100 million light years is the distance scale marked here. And you see these fuzzy objects, this pattern, filament and void kind of objects, looks like cloudy things. Every molecule of this cloud would be a galaxy. And you go further away, 1 billion light year length scale I have marked here. And its structure looks very interesting now, because you see this is, microstructure is clear. There's something in microstructure, small level. Micro, I mean here, length scale of 1 billion light year. That's what I call micro in this case. But you see, if you draw a circle of this kind of big, say 10 billion light years, the average area here, average area anywhere in this region you see is the same. Is the same. So on the average, things look same. This is the observed universe. About 200 billion galaxies in observable universe. Each galaxy has 100 billion stars with 200 billion galaxies. But you see that on the average, the universe looks the same. This is a very important property of theories of our universe. The universe is homogeneous and isotropic. It's the same everywhere and looks same in every direction. Homogeneous and isotropic universe. This observation of homogeneity and isotropy of the universe forms the basis for our standard model of cosmology. So idea is, so we construct theories that the universe started with a hot and dense plasma of elementary particles with almost uniform density. There were tiny, very tiny density fluctuations initially, which later grew due to gravity and led to galaxies, clusters of galaxies, etc., leading to the structure in the universe. You have to make theories in which there are very tiny fluctuations. If fluctuations were larger, everything will turn to black hole. We know this thing. We can calculate it. So we know the structure today. So we know that density fluctuation has to be extremely tiny. 1 part in 10 power 5. 1 part in 10 to the power 5. If that's how tiny density fluctuation has to be there. Now, how did this fluctuation originate is a fundamental problem of the theory of universe. It used to be an unsolved problem. Now we have come to remarkably close to the solution of this thing. And what we have understood is these resulted from quantum fluctuation of the vacuum during the earliest stages of the universe. Now, I'll tell you about that. So our whole structure actually in the universe arose from quantum fluctuations of vacuum. So let's get the Big Bang theory of the universe basic picture. The whole Big Bang theory of the universe is based on a single most important observed fact. This was an observation made by Edwin Hubble in 1929. That observation showed that all galaxies are moving away from each other. He used Doppler shift of spectral lines. We know that if there is a light source is moving away from you, then the wavelength shift toward larger wavelength. We call it red shift. If they're coming towards you, its wavelength shift to a shorter wavelength called blue shift. And he found that most observed galaxies showed Doppler shift towards larger wavelength, meaning that those galaxies are moving away from us. He also found that galaxies which were farther away are moving away with larger velocities. So he made a law. From the observations, he derived an equation. He found a linear relationship between the distance d and the recession velocity v of a galaxy. How fast galaxy is moving away from you was simply proportional to the distance of the galaxy. V equal to h times d, called Hubble's law. H is called the Hubble's constant. Its value is simply 70 kilometers per second per megaparsec. 1 parsec is a distance unit, 3.3 light years. Megaparsec is 3.3 million light years. So you see, if you put a galaxy at a distance of 3.3 million light years, that will be 1 megaparsec from us, it will be moving with a distance velocity of 70 kilometers per second. That's what it means. H is 70 kilometers per second per megaparsec times d is 1 megaparsec. So V is 70 kilometers per second. A galaxy twice the distance, 6.6 million light years, will be moving away twice the velocity, 140 kilometers per second, and so on. That's the Hubble's law. So every galaxy is moving away from us. It looks like as if we are at the center of the universe. It is not. It is observers at every galaxy will see exactly the same thing. Universe is homogeneous, I just told you. So let me give you a little bit picture of this thing. We consider a two-dimensional example of a flat expanding space. I have used the term flat here for a very important reason. I have no time, but you can learn about it from internet, that Einstein's theory of relativity actually changes the concept of gravity altogether. Our space can be curved and all that. I'll not get into any of that, because it turns out observations tell that our space is flat. Just you are familiar with Euclidean space, x, y, z coordinates. So it's completely fine. So imagine a three-dimensional thing is very difficult to draw. I have given two dimensions. So suppose this was our space. I've just marked a small part of it, space sheet, and you mark the dots as galaxies. These black dots are the galaxies at time equal to t1. So expansion of the universe means that after a time, which is time equal to t2, which is greater than time t1, universe expands. It's just simply like stretching the rubber sheet. Stretching the rubber sheet. So if you were sitting on the first galaxy, second galaxy has moved some distance, time is t2 minus t1, you calculate velocity. You can immediately see that a galaxy which is twice far away, it would have moved twice the distance in that much time. So its velocity would be twice large. So you'll get the Hubble's law immediately from this, and you can also see that the same will be obtained wherever you are sitting. You sit on this galaxy, this is whole infinite sheet. I have only drawn a small part. So infinite sheet. So wherever you sit, it's going to be the exactly same observation. This is the general picture of this. It's very important to realize that I am calling it stretching of rubber sheet, not calling the galaxies are moving away. It's a fundamental important property of Einstein's universe, Einstein's theory, that space can become dynamical. Space can stretch. We don't say galaxies are moving away from each other. We say space between galaxies is stretching. So how do you mark it? How do we characterize expansion of the space? We say the universe expands like this rubber sheet. In 3 dimensions, it will be like rubber cube. And which is being stretched uniformly by a single factor, we call it scale factor R of t. So you simply take a rubber sheet, stretch it by factor 2. So all distances multiplied by factor 2, scale factor has changed by factor 2. Single space. So because changing in every direction same way. So you don't want to say X changes by this amount, Y changes by this amount. Every direction changes by same amount, so single scale factor, you mark it. We'll remember the scale factor, this will come in our equation. Now, the observation of the expansion of the universe combined with Einstein's theory of gravity, which is general relativity, leads to a remarkable conclusion. The universe was extremely small in the beginning. And actually, if you keep going back, apply Einstein's equation and keep going back in time, how small it was, it started from a singularity with extremely high density. Singularity normally means infinite density, but what we will mean here is extraordinarily high density. It's high density and temperature, and it kept expanding until now. Initial expansion was extremely fast. It's some sense like a gigantic explosion. This is the Big Bang theory of the universe. That started from extremely tiny region, started expanding extremely fast, like a gigantic explosion. We call it Big Bang theory of the universe. Now, I'll use only one or two equations. These are very simple equations. Using observations and applying Einstein's general relativity to the universe tells us how the universe has been expanding. So I write it here equation. I define h square is equal to, this r is the scale factor I told you. How universe has been stretching, how the rubber sheet has been stretching. So if you know r, you would like to know r dot. R dot will tell you how fast it is stretching, the velocity of stretching. So the equation is the following: r dot by r square is the following thing: 8 pi g rho by 3 plus lambda c squared by 3. R of t I told you is scale factor, stretching rubber sheet. So all physical distances are proportional to r of t. So if r of t increases in time, distances between various objects will be increasing in time, and we call it expanding universe. If r was decreasing, it will be collapsing universe. Our universe is expanding. No. Rho is the mass energy density of the universe. G is Newton's constant. C is speed of light. Rho is the mass energy density of the universe. And lambda is a very important constant. It is known as a cosmological constant. We don't know its value. It could be zero, it could be non-zero. But this constant is present. So we'll remember this equation. Now let's try to understand this equation and let's make meaning of this thing. So you see, physical distances are proportional to r of t. So dr by dt will give the velocity v up to some proportionally constant, and r of t will give the distance, physical distance, up to proportionally constant. So h is 1 by r dr by dt, so it becomes v by d. If dr by dt is velocity, and 1 by r is d, proportional to d. So you get v by d. H is v by d. So v equal to hd. Remember, this is the Hubble's law we wrote down. Velocity is proportional to distance. So a galaxy, if you calculate the distance of a velocity, how a galaxy is moving away from you, is velocity given by h times v. Only thing is that h was a constant there. I gave you Hubble's constant value. Here h is defined to be this, the right hand side. And here the lambda is the constant, but rho is density, mass energy density of the universe will change. So h keeps changing. Actually, h does change. The Hubble constant, when I gave you 70 kilometers per second per megaparsec, is the value at present. This value was much larger earlier, very long time ago. Very, very long time ago. Now, one important thing we learned here from here, very important thing. Look at the right-hand side of the equation, 8 pi g rho by 3 plus lambda. Lambda is a constant, c is a constant. Rho is the only thing which changes in time. It's a mass energy density. If the universe expands, things dilute, gas dilutes. But suppose for some reason, there is some kind of energy which is constant. Suppose rho was constant, energy density. How it's constant, we'll discuss that. Then there is no difference between these two terms. Both are constant. There's numerical values. So their behavior would be same. Their numerical values may be different, their behavior is exactly the same. Important thing is, cosmological constant is just like a constant energy density. This is a very important thing, we should remember that. The cosmological constant lambda is just like a constant energy density. Now we know that all bodies attract each other by force of gravity. So universe is expanding, galaxies are moving away from each other, that's fine. They must have some initial velocity, but they should slow down. If you throw a stone up from Earth, surface of Earth, it goes away from Earth, even though Earth is attracting, but it slows down, we know that. So galaxies can move away from each other due to some initial velocity, but they must slow down. So universe expansion must decelerate. How do we calculate acceleration? I go the equation for velocity. We need velocity for acceleration. That will need equation for d2r by dt square. This is my last equation. There will be no more equations after that. So 1 by r d2r by dt square. This is acceleration equation for expansion. This is very interesting equation. This is minus 4 pi g by 3 rho plus 3p. Rho is the mass energy density, p is the pressure of the system. And lambda, same cosmological constant. Now, what do we expect? We expect deceleration. Gravity is attractive, so universe expansion must slow down. So we expect deceleration. We expect right hand side should be negative. d2r by dt square should be negative. Of course, normal matter, energy density is positive, pressure is positive, we know. So if you neglect lambda, then right hand side is negative indeed. So if a normal matter, if you have an ordinary gas, hydrogen gas, or whatever gas you have, then the universe would be slowing down, no question about that. And you will get decelerating universe. It turns out there are certain systems that even though they have positive energy density, pressure can be negative. This is a very, it's not an exotic thing at all. You can even have a condensed matter system where pressure can be negative. And there will be other things for which pressure can be negative. And if pressure is sufficiently negative, then forget lambda right now, then rho plus 3p can become negative. If rho plus 3p becomes negative, right hand side becomes positive. That is very funny. Then right hand side becomes positive, the universe expansion accelerates. So galaxies will be moving away from each other. dr by dt gives you velocity, but d2r by dt square becomes positive, so they are accelerating away from you. Now same thing will happen if lambda was positive and it dominates right hand side, because lambda comes with positive term. If lambda is positive with a constant, then again you will get acceleration. Now this is a very surprising conclusion. How can universe expansion accelerate when galaxies attract each other by force of gravity? Gravity force we know is attractive. This is only possible if the force between bodies becomes repulsive. You see, it's like that you throw stone up and it goes away, but its velocity upward keeps increasing faster and faster. That's only possible if Earth is repelling the stone, not attracting. So what this means is that when I said here that if right hand side is positive, rho plus Cp becomes negative, or lambda cosmological constant, then positive cosmological constant or constant energy density, which is same as cosmological constant, it leads to repulsive gravity. This is also called dark energy. So dark energy is the situation when the gravity becomes repulsive and expansion actually accelerates. Observations now show that indeed the universe is accelerating at present. This was a very surprising result. Nobody expected this. People knew that the universe could be slowing down, but they found the universe is accelerating. So actually there is a dark energy present in the universe, or a cosmological constant is present in the universe. 2011 Nobel Prize for Dark Energy was given to Perlmutter, Schmidt, and Rees. In the observations, people have made detailed observations. They also show that dark energy and accelerated part of the universe started happening in last about 4 billion years. The universe is about 14 billion years old. Only in 4 billion years ago it is happening. Before that, universe was dominated by normal matter. And it was decelerating as you expect from attractive gravity. Only in last 4 billion years, it has been accelerating. Now, we address the issue of what is the dark energy. So we concluded the dark energy is the constant energy density filling the whole space, which is same as the cosmological constant. When can you have a constant energy density in the whole space? This cannot be energy in the form of any gas or particle, as then energy density will decrease during increase of volume, due to dilution of particle number density. You take a gas and expand the volume, energy density decreases of the system. Let's ask the question, what do we expect when there are no particles at all? Nothing, no gas, nothing. We call it a vacuum normally. Out space, we say out space is the vacuum basically. Nothing else is there. But vacuum means nothing is there, so it should have zero energy density. We want constant energy density, but zero energy density, not zero energy density. If you put rho equal to 0, lambda everything is 0, then the thing 0. But that's not so obvious. Let's not be very hasty in concluding that vacuum means nothing is there. Quantum physics always has surprises. Now let's recall what we understand about vacuum. Vacuum means, by definition, lowest energy of a system. Lowest energy of system is called vacuum. Remember 0 point energy of harmonic oscillator? In the ground state, n plus 1 half h bar omega for one dimensional oscillator. N equal to 0, half h bar omega still is there. 0 point energy. The ground state energy is not 0. Casimir effect. If you know about this, Casimir effect comes from vacuum fluctuation of electromagnetic field. In vacuum, you expect E equal to 0, B equal to 0, nothing should be there. But there is some vacuum fluctuation. Even if there is no electric field, magnetic field you put there is a vacuum fluctuation, and that leads to very real force for Casimir force actually. We know that the particle-antiparticle pairs can be produced from vacuum. Now, how do you produce particle-antiparticles when there is no incoming photon or something like that, say electron-positron pair, because it violates energy conservation. You have to create 0.5 MeV is energy mass of one electron, so electron-positron will call 1.1 MeV. How do you create such a pair? But we also know quantum mechanics has energy-time uncertainty relation. You can violate energy conservation for very short time if delta E, delta T is greater than h bar by 2. So you can create a particle-antiparticle pair for very short time, it can re-annihilate, and there is no problem. And this process keeps happening. This is called vacuum fluctuation. So vacuum is not really empty. It has all these fluctuations of all the fields, particle-antiparticle pair production, everything. If all these things are happening, how do you know vacuum has zero energy density? No, not at all. In fact, we cannot make this conclusion. If value should be governed by elementary particle interaction, of course, what we know is it should be constant during expansion of the universe, because its value should be dependent on how particle-antiparticles are produced by fluctuation. It's quantum field theory. So it has nothing to do with universe expansion. So its value should be constant. So now if vacuum had an energy density, it will have energy density which is constant during expansion of the universe. This is exactly the property we discussed for dark energy and cosmological constant. So vacuum energy will contribute to dark energy and hence to cosmological constant lambda. That is the thing we learned. Now you can calculate, you can try to calculate vacuum energy using quantum field theory. We know techniques of quantum field theory you can calculate. And then idea is simple, you calculate, match with the observed value of dark energy, that will be great. And that will give you cosmological constant at present. What people have observed, they got Nobel Prize for that. The problem is any estimate you make, typically people make dimensional estimates for that. All estimates from particle physics theories, using all renormalization theories and whatever you want to make, they lead to extraordinarily large value of cosmological constant. 10 to the power up to, it can be small, up to 10 to the power 120 times larger than the observed value. I mean, it's way off, completely. You are nowhere close. So this is the most important unsolved problem in cosmology. Why cosmological constant lambda is so small? It is called the cosmological constant problem. And there is a huge amount of work going on that, and people have been working for ages on that. Quantum gravity is one of the most important things you need for that. String theory is the primary candidate. Loop quantum gravity, Poset approach to quantum gravity. There are various approaches, and people have different propositions for that, but it remains unsolved problem, cosmological constant. Now, you also must have heard, if you know about dark energy, there is a dark matter also there. Dark energy, dark matter are fundamentally different. No relation like equal to mc square between them. They're fundamentally different objects. I told you dark energy is an exotic form of energy, possibly vacuum energy or cosmological constant, will lead to repulsive gravity. Dark matter is actually any matter in the universe which does not emit its own light. For example, planets are dark matter. We all are dark matter. We don't emit light. So for all the racist people in the world, we are all dark. Sun is not dark matter. It's luminous, what's called, because it emits light, and huge amount of light, produces light. So stars are part of what's called luminous matter in the universe. Why are we talking about dark matter? Because galaxy rotation curves. These are curves for velocities of objects which are orbiting the galaxies at large distances. Molecular clouds and stars and all those things. These observations showed that amount of dark matter in the universe is almost 5 times more than the amount of ordinary luminous matter in the universe. So I will not give you this derivation in this case. It's just that this dark matter which is present in the galaxies, it could very well be, maybe I have put somewhere, okay, no, this is okay. Yeah. So, so the universe consists of different forms of energy and matter. 5% is ordinary matter from which stars and planets, etc. are made up of. We are all made up of that. Electron, proton, neutron, and things like that. 72% is that dark energy or the cosmological constant. We don't know what it is. It's something constant, some constant energy density in the universe filling up the whole universe. But 23% is dark matter. We don't know what it is. It could be very well like a small planet-like object which don't emit their own light, or it could be primordial black holes. These are supposed to be black holes which were formed in the early universe, not by collapse of stars and things like that, which is what is believed to be star formation present. Or it can be composed of new types of exotic particles which are yet to be discovered. This is a frontier area of research in high energy physics. A lot of particle physicists are working on that. The idea is that you try to determine what are the properties required for this dark matter particle and look for them in collider experiments. or in deep underground laboratories, or if they are annihilating in the universe somewhere, then what emission they will be doing, detect for that thing. So all these kind of experiments are going on. There is a huge search going on for these. So the Big Bang theory, let's start with some basic picture of Big Bang theory. The universe was born 13.7 billion years ago. The earliest stage of the universe is called the Planck stage. We don't want to talk about before that, but this is this stage occurred when universe was 10 to the minus 43 seconds old after the Big Bang. Big Bang is the time when of initial singularity. We call it t equal to 0. At Planck stage, the universe density was 10 power 87 tons per centimeter cube. Now, you may have not even idea that you don't have an idea about this. It's like this. It was incredibly hot. Temperature was 10 power 32 Kelvin. You know the core temperature in the core of the sun is 10 power 6 Kelvin. 10 power 6 Kelvin. This 10 power 32 Kelvin we're talking about. Now, we don't have a theory for times earlier than the Planck stage. It requires quantum gravity theory, so we don't talk about earlier stages. Now, this density is 10 power 87 tons per centimeter cube is huge. Just to give you an idea, you probably have held lead in your hand, which is 10 grams per centimeter cube. 10 grams per centimeter. The universe at present contains neutron stars, which we can observe. They have density of 10 power 8 tons per centimeter cube. It's like compressing a 10-kilometer high mountain to the side of a cricket ball. We are talking about 10 power 87 tons per centimeter cube. So that was initial density and very, very hot. So let us understand the implication of the statement that the universe was so small and dense in the beginning. So this is the galaxies at present. I have marked them like that, very far away, about 1 million light years away. The universe has been expanding, so that means they were closer earlier. So I have marked them closer earlier. Keep going back down earlier using Einstein's equation. Einstein's equation I gave you, they tell you how the universe has been expanding. So you can keep applying that equation. What about the earlier times? Galaxies will have to overlap. Now, overlapping galaxies doesn't seem to be a problem. The galaxies are vastly empty space and stars here and there. But what will happen is you keep applying that equation, the stars will have to overlap. In fact, every whole observed universe will become smaller than a single star size, and even much smaller than that. Much smaller than that. I'll tell you about how small it is. How do stars overlap? How can you put 200 billion stars on top of each other? Actually, it's not stars. Because what happened long time ago, stars and planets, etc., formed from large clouds of hot gas. Our solar system formed because there was a large cloud of gas which condensed. Central part became star, remaining part became galaxy. Galaxies themselves were huge clouds. And clouds certainly can overlap. They just become more dense. So at very early time, the universe consisted of huge amount of hot gas everywhere. And at even earlier time, the gas was hotter and denser. That's what you need. It was hotter and denser. So early universe was filled with hot gas, but this gas could not be completely uniform. Remember, I mean, this has to be patchy, because the way it was denser, those things became dense and more dense, and where it was less density, they became void. Otherwise, you won't get structure. A uniform density gas will simply, in expansion, will remain uniform. You won't get galaxies and stars. These are the density fluctuations I've been talking about, and I'll tell you later. They were produced due to quantum fluctuations. So the early universe was very hot. Age of the universe at present is 13.7 billion years, very cold. If you go in space, the temperature you will feel is about 3 Kelvin. That's the temperature of something called background radiation. I'll tell you about that. If you keep going back, universe was much smaller and much denser. Highly compressed, extremely hot gas. If you compress a gas, adiabatically, it becomes hot. It's adiabatic expansion because the universe cannot exchange heat between things. So when the age of the universe was about 300,000 years from the time of Big Bang, singularity in the beginning, its temperature was 10,000 Kelvin. You can write in few electron volts. 1 electron volt is given this 1.1 times 10 power 4 Kelvin. So now when temperature reaches few Kelvin, few electron volts, you know that the binding energy of electrons in atoms is few electron volts. So at temperature higher than that, electrons would not remain bound to nucleus. Gas becomes ionized. Hydrogen, helium, all the gases become ionized. You keep going back time, it becomes denser gas because it's even smaller. Temperature becomes much higher. Temperature becomes 10 power 10 Kelvin. In energy scale, it becomes MeV. Okay. Now, if you know a little bit nuclear physics, you know that the binding energy of proton-neutron in nucleus is few MeV. So when temperature becomes higher than few MeV, nuclei will break. They cannot remain there. So temperatures earlier than that and times earlier than that, few seconds, there were no nucleus. It was only consisting of protons and neutrons and electrons and all that. Keep going further back in time, when age of the universe was microsecond, its temperature was above 100 MeV, and this is something we have learned, some theory, that at such temperature, and now we have learned it also from heavy ion collision experiments, that above temperatures of 100 MeV or 10 per 12 Kelvin, protons and neutrons also break. You know, protons and neutrons are made up of quarks, gluons, elementary particles. They melt into a plasma of quarks and gluons. This is the stage. So when the universe was younger than a microsecond, it consisted of hot plasma of elementary particles. There was no composite structure at all. Nothing, no bound state, nothing. Only elementary particles. So the quark-gluon plasma, quarks and gluons, plasma of other particles, the electrons, photons, and all that. This is very interesting because this is exactly the kind of system we are able to study in laboratory at present, using what is called ultra-relativistic heavy ion collision experiments. So these are large experiments going on where heavy nuclei like lead or gold are collided at very, very high energy. So when they collide at such high energy, the protons and neutrons break into quarks and gluons, and they thermalize. A huge amount of quarks and gluons are produced also, and they thermalize, and they lead to what is called quark-gluon plasma. So you get quark-gluon plasma exactly like what I was telling you when the universe was microsecond old. So you are able to recreate that stage of the universe in laboratory. Here you can study its properties. It's happening at the relativistic heavy ion collider at Brookhaven National Laboratory, USA, and Large Hadron Collider at CERN. Now, these are very exciting experiments. We are recreating temperature energy densities which were present in the early universe when its age was few microseconds. So you will be able to study quark hadron phase transition, how quarks and gluons convert into protons and neutrons. This phase transition occurred in the early universe. Now you can study in controlled laboratory experiments people have been doing. This is one of the areas I work in fact. It directly tells us, you study the phase transition here, this system, you know what was happening in the universe earlier. It's very important because that can have very important implications for the evolution of the universe. So what was happening at microsecond in the universe, you are able to study in laboratory here. Now, quark hadron transition is the only phase transition of elementary particle physics of the universe which can be studied in laboratory conditions as present. Elementary particle. Other transition you study, water to steam, that's not elementary particle, that's molecule. One hope is with, again, people are looking into that, if glimpses of something called electroweak phase transition can be seen in laboratory, that will be fantastic. But now, understanding these early stages is crucial to understanding how the universe evolved. Now, matter at the early stages consists of hot plasma of elementary particles, I have told you. Their properties and interaction have to be understood to investigate these stages using Einstein's equation. Recall, Einstein's equation I gave you, rate of change of expansion. Remember this equation, the same equation I gave you earlier. How a universe is accelerating or decelerating is given by this equation. You need to know pressure. Just knowing elementary particle is not good enough because that gives you energy density. You need to know pressure between them. Pressure needs interaction between particles. Remember van der Waals equation for gases? Molecular attraction changes pressure. So pressure requires interaction. So you must understand particle interaction. This is how whole elementary particle physics theory gets intertwined with the theory of the universe. You must understand elementary particles, must study their interaction, then only you know how universe has been expanding, otherwise you don't. The particle physics theories play a very crucial role in the early universe. Modern particle theory, physics theories are based on unification of forces. You may have heard the word, we can't discuss it. It tells us, these theories tell us the history of the early universe has been full of exciting events. The universe was very hot, it has been cooling down. Now, you know condensed matter systems. When condensed matter systems you take and you cool them down, they change, their properties change. You have normal metal becoming superconductor. You have steam converting to water, water converting to ice. So when systems cool, temperature changes, it can undergo phase transition. Exactly same thing has been happening in the universe. And to understand phase transition, we know from statistical mechanics, you need to know interactions of basic constituents. So interactions of elementary particles have to be understood to know the nature of phase transition. This is a very exciting area of research in astroparticle physics. You work out relativistic quantum field theory with the full interactions and all that, and work out what kind of phase transition have been happening in the universe. And these phase transitions can dramatically change the course of evolution of the universe. Some of these transitions, and just give you glimpses of that, have changed the properties of matter in the universe drastically. You may have heard the Higgs boson when it was discovered. It was a big thing that Higgs boson gives mass. It happened during a phase transition. This whole thing happened in a phase transition. This is called electroweak phase transition. And people can work out in the early universe, there was a phase transition and the mass generation of the particle happened. Hadron formation from QGP. I told you microsecond earlier, it was only quarks and gluons, but eventually when the universe cooled down, there were hadrons, protons and neutrons. This happened in what's called QCD phase transition. Eventually, there were other important stages, formation of nuclei, protons and neutrons combined to form nucleus, and the neutral atom formation of that. One of the most important things which happened during a phase transition is matter-antimatter asymmetry, called baryon asymmetry of the universe. This is an unsolved problem at present, one of the frontier unsolved problems of cosmology. At present, we have very little antimatter. Whatever you see outside is planets and all those things made of protons, neutrons, electrons. Very little antiprotons, very little antineutrons, very little positrons. Now, this is very surprising because you can show from particle physics theory that initial universe must be matter-antimatter asymmetric. Matter-antimatter symmetric. Matter-antimatter must be present in equal amount. It's very, very hard to make them asymmetric. It's very unnatural theories you have to invoke for that. All theories tell you that matter-antimatter must be symmetric in the very early universe. So what happened later? What happened to all the antimatter? They went away. Why matter became dominant? This is called baryon asymmetry or matter-antimatter asymmetry problem of the universe. It's an unsolved problem. And huge amount of research is going on that. Now recall, condensed matter phase transitions, something very interesting can happen. Not that a phase transition, very interesting objects can form. Superfluid phase transition, superfluid vortices can form. These are the line-like vortices. Superconductors, again, line-like vortices. Flux tubes can form. Liquid crystal phase transition. This is something which I work on. Strings and monopoles can form. Monopoles are point-like objects, small, tiny, ball-like, little ball-like objects. Strings, again, wire-like objects. These are called topological effects for a very important reason. These can also form in the universe during phase transition. Phase transition, for condensed matter system, every phase transition doesn't produce this. I give you very specific examples. It turns out in the universe also there are many phase transitions. In some of those phase transitions, some of these objects and similar objects can form. Difference is condensed matter system is a non-relativistic system. In universe, we have a relativistic system. Very high energy densities we are talking about. So it changes the scale of these things completely. We have these objects, possibility of formation of these objects, and there is huge research going on to detect if these were formed. They can be cosmic strings, and their properties are astonishing. If they're cosmic strings, the thickness will be 10 to minus 29 centimeters. That's like zero thickness. You can't see it, so thin. But the mass density will be 10 per 16 tons per centimeter. These are mind-boggling numbers, 10 per 16 tons per centimeter. There will be domain walls, sheet-like objects, 10 per 46 tons per centimeter square. A micron-sized wall will have same mass as the mass of the entire galaxy. Magnetic monopoles, 10 per 16 times heavier than a proton. So the domain walls are so heavy that they are observations they are ruled out. If they were there, you would have seen them. But cosmic strings and magnetic monopoles can very well be there, and a lot of research is going on trying to detect those objects. If you find them, they'll get direct window into the very early universe when these objects were formed. It's a very exciting area of research, actually. Now there's something interesting. I told you dark energy is there at present, and I also told you it has been dominating in only last 4 billion years. Before that, it was not dominating at all. Before that, it was normal matter, and universe was decelerating. At present, it has been accelerating. It turns out that there was a dark energy at the birth of universe also. Modern theories of limited particle-phase interaction show, in fact, they are made that such way, that during a very short period, at a very, very early stage, this is only 10 to minus 35 seconds after Big Bang, the energy density could almost be a constant. Now remember, energy density could almost be constant, but like cosmological constant. And when the energy density becomes constant, I told you it becomes universe accelerates, doesn't decelerate. So the constant energy density behaved, recall, almost like cosmological constant and gave accelerated expansion. See, just like the dark energy at present, except that this dark energy was very, very large at that point, extraordinarily large magnitude. Due to this, the universe expanded extremely rapidly, exponentially. So actually, I'm sorry, I bring back that equation again. It's the same equation, no new equation, but same equation again about the expansion of the rate, expansion rate. R was scale factor telling you how the distances are related. R dot gives the velocity of expansion. So this was the equation. R dot by R square is right hand side. Now, if energy density is constant, lambda is anyway constant. Suppose energy density rho is constant, I'm telling you, dark energy, the whole right hand side is constant. call it some kappa square. It's a constant. This is a very simple equation. You can solve it. R dot by R equal to kappa. dr by dt by 1 by r is kappa. So dr by r is kappa dt. Simple solution is the log r is kappa dt is exponential kappa dt, or r of t becomes r of t naught exponential kappa t minus t naught. This is the solution for this equation. This is telling you that this is exponential expansion. So whenever energy density is constant, expansion is like that, exponential. But why don't we see it today? I mean, I say dark energy is there present at present. That's because this kappa t, kappa is very, very small at present. Energy density is incredibly tiny. Cosmological constant also is very incredibly tiny. So for whatever time scale we are dealing with right now, kappa t is very small. If exponential kappa t is there and kappa t is very small, then it is like a linear expansion. So universe at present is undergoing something like linear expansion. In the beginning of the universe, kappa t was extraordinarily large. T was short indeed, time scale was short, but kappa was extraordinarily large. Rho was extraordinarily large. Lambda would be very small again, but so the term became exponential, literally exponentially rising. So universe expanded exponentially. And this is called, and this lasted for a short time, but it changed the whole universe completely. This is called the inflationary stage of the universe. Due to that inflationary stage of the universe expanded very, very rapidly, and our whole observed universe, 90 billion light years across, was smaller than a micron when inflation began. A micron size, so we all have forget about star size or something. We came from micron size object. And this stage has been most crucial in the history of the universe. Series of elementary particles show that microscopic density fluctuations were generated due to quantum effect at that time. See, what happened is, the expansion was so rapid, exponential expansion, the universe cooled. Expansion of the universe cools the universe. A gas expands, it cools. The universe has been cooling down. Exponential expansion, whatever was there earlier in the universe, cooled so rapidly that temperature becomes zero literally. Even at that early time. So you see, we started very hot, 10 power 32 Kelvin, but the universe exponentially expanded and it cooled down to zero temperature. What was it filled with at that point? It was filled in the vacuum state because there was no particle. That's what we call vacuum. No particle, vacuum. But it was not just vacuum. There was a constant energy density which was very large. I told you, it was very large. That's what gave you exponential expansion. Constant energy density was filling it, but no particles of any kind. And when there is a vacuum like that, there's no particles, anything, there will be quantum fluctuation. Vacuum always has quantum fluctuation. So there were only quantum fluctuations present at that time. So people can calculate that quantum fluctuation. Now, eventually what happened that constant energy density decayed. That's what people study. The energy decayed into producing lots of particles. And the universe got filled with hot plasma of elementary particles. So the constant energy decaying into and producing hot plasma of particles, we call it reheating of the universe after inflation. Once the constant energy density decayed and the plasma of elementary particles energy density starts changing in time, starts diluting, inflation ends. No more exponential expansion. But inflation has left its footprint. Because there were quantum fluctuations of the vacuum during inflation, and they got imprinted on the density of plasma. The plasma would have been otherwise completely uniform because completely uniform density. The energy density was constant and uniform everywhere. So plasma it produced was completely constant energy density plasma. But no, because there were vacuum fluctuations top of that constant energy density. Vacuum fluctuation. These vacuum fluctuations got imprinted on the density of plasma. So this is the universe now we got in the end of the inflation. Almost uniform density plasma with microscopic density fluctuation, which was generated due to quantum effects during inflation. Later on, these are the density fluctuations which led to formation of what we see in the galaxy today. Galaxy cluster of galaxies, etc. Without such fluctuation, the universe would have been filled today only with an extremely dilute, completely uniform cold gas. Important thing, we can study the structure today. We can study the imprints of these density fluctuation and find and determine, calculate that what were the properties of the steep density fluctuation needed. This provides a direct test of theories of inflation. Inflation happened so long ago that 10 power minus 35 seconds after the universe was born. Nothing you could know about it. But present day observations are telling you how to check those theories. This is one of the most active areas of research in cosmology and astroparticle theory. To use present day observations to constrain quantum fluctuations of the vacuum during the inflationary stage. Now, of course, there were not just fluctuations in this constant energy density, there was quantum fluctuation in the gravitational field also. There was gravitational field present. Whenever you have mass energy density, there is gravitational field. So there were quantum fluctuations in the, in fact, even in a vacuum, there is a gravitational field. which is 0, but there will always be quantum fluctuations of the gravitational vacuum in the gravitational field. So there were gravitational field fluctuations in gravitational field itself during inflation, and these quantum fluctuations in gravitational field became gravitational waves later on. So we at present are trying to detect that. These will be primordial gravitational waves. You must have heard that we have detected gravitational waves coming from collision of black holes, collision of neutron stars. But there is supposed to be a background of primordial gravitational waves which came from quantum fluctuations of gravitational field during inflation. Just like matter was born by two quantum fluctuations in the vacuum of the constant energy density. And they search on for these primordial gravitational waves. Now another very important thing, very straightforward, prediction of Big Bang theory is, remember, every hot thing emits light. So when an iron rod becomes hot, it glows red. When it is hotter, it becomes yellow and then becomes bluish. Big Bang theory predicts the universe was extremely hot in the early stages. So it must have been filled with bright light. Indeed, it was. As the universe cooled, light would have cooled. And cooling light means its energy decreasing. Energy decreasing means wavelength becoming larger. So light would have undergone reddish with larger wavelength. And we can calculate at present that if the light, whatever electromagnetic wave is present, it should be present in microwave. This is the same as one uses for mobiles and television. In the same wavelength regime, there is the electromagnetic wave, light, coming from the early universe, remember. This was known as cosmic microwave background radiation. This was discovered by Penzias and Wilson in 1965, and they got Nobel Prize in 1970. And this was the picture they got, completely uniform. This white thing in the middle is because of galaxy, our galaxy, dust blocking this. Otherwise, completely uniform because their resolution was not very good. Now, one thing I would like to tell you is the old days, we used to have televisions which were not LCD, LED, they were picture tubes. And when cable signal will go away, there will be white dots on the screen. If you have access to these monitors, you can look at it. Turn off the signal and turn on the TV only. You'll see white dots flickering. I told you TV signal in microwave regime. So this TV, your TV should also be receiving these microwave coming from the early universe. Indeed, it does. And whatever dots you see on the screen, 1% of that white dots, because snow, is due to cosmic microwave background radiation. So it's a very good feeling, it's exciting feeling. You turn on this TV without any signal, and what you see on the screen, 1% of that you are actually detecting directly from the birth of the universe. Very remarkable feeling. Now, microwave background radiation cannot be completely uniform because initial gas was lumpy. I told you there was density fluctuation. Somewhere it was denser, somewhere it was lighter. So denser means hotter, lighter means cooler. So that means microwave background radiation also cannot have same intensity everywhere, cannot have same temperature in all directions. It's a black body temperature, completely perfectly like a black body, but black body temperature has to be different. These are called cosmic microwave background radiation fluctuations. So they track down the density fluctuation in the very early universe. Those generated as quantum fluctuation during inflation, remember, I told you. This was detected. This was a much finer resolution picture obtained by Kobe satellite, data 1992. Nobel Prize was given in 2006 to Method and Smoot. So red is hotter and blue is cooler. And this is a very tiny fluctuation. This is 1 part in 10 power 6 microkelvin fluctuation. Temperature of the black body is at 2.7 Kelvin at present. And this is a microkelvin fluctuation. So very, very precise measurement has to be done. Then only one could find these fluctuations. Later measurements gave you even finer resolution, and this is microwave fluctuation observed by WMAP satellite. The latest data is this. This is given by Planck satellite. And this gives incredibly detailed information about primordial density fluctuation. You see, what happens is that you see structure here. There's something structure. It's not a uniform dot. This brown or reddish dots and bluish dots, which are hotter and cooler portions, are showing some patterns here. These patterns are extremely important because they are containing in them statistical properties of the density fluctuation of the original gas, original plasma. Because plasma was hotter and cooler, that's how the initial radiation was hotter and cooler. That's what you are seeing today. So by studying the statistics of these fluctuations, you know what were the original density fluctuations. This gives you much better number than by studying galaxies, etc. Because the galaxies undergo much kind of dynamics. But cosmic microwave background radiation gives you the nature of density fluctuation present right at a very early stages. And by studying this, people are able to constrain models of inflation, which occurred when universe was temperature minus 35 seconds old. In fact, I can tell you one thing. Before the inflation model was given, this was a very unsolved problem, how density fluctuation came about. And people had exotic models for that. I told you about cosmic strings, 16 tons per centimeter length per centimeter was the mass density of cosmic strings. And there were models of, I also worked on that, models of cosmic string based density fluctuation. These are heavy strings, so they can give density fluctuation. They give a pattern of these kind of dots, which is way off, completely off. So this cosmic microwave background radiation data was used to reject that model. This was really remarkable. Cosmic string-based structure formation model has been ruled out by these things, and the thing which is surviving and in excellent agreement is the density fluctuation model predicted by inflation, which only happened in 35 seconds. So this is the basic picture. I'll close here. This is basic picture of the universe. Present day observations are being used to constrain theories of very, very early universe. That's very important. I'll close here. Thank you.
Okay, thank you, Professor Srivastav. Now the session is open for the questions. I can see there are a few questions already marked in the chat box. So I will just read it out and probably you can answer them.
Sure.
Okay. So first question, Smriti Pragya has asked, how every galaxy will see exactly same things or same distance and velocity? A general theory of relativity must come to play, since there must be different gravity for different stars and planets in a galaxy.
Yeah, I mean, you have to always take into account of local structure. For example, when we study the motion of galaxies away from us, when Edwin Hubble observed how galaxies are moving away from us by observing redshift, you have to worry about how our planet Earth is moving around Sun, because it also has a velocity. Also, the neighboring galaxies also attract other galaxies. So in fact, he did not observe that all galaxies are moving away from us. Some of the galaxies, in fact, we know Andromeda galaxy, which is the nearest galaxy, is not moving away, it's coming towards us. So that's because our galaxy and Andromeda galaxy have become bound, gravitationally bound. So it is indeed, it is very important to worry about these local effects. Local effects are present in every galaxy, so you have to filter out those effects. You filter out the effects of the local star system, local solar system, local stars, local galaxies, local cluster of galaxies, and remove those effects, then whatever remains is the velocity we are talking about. So you have to do a lot of work. It's not a very simple observation.
All right, I think that clarifies the question. So there is another question. I'm not able to take all the questions. I'm just taking some random questions. Somebody has asked. This is Ninsa Manashuni. Maybe I'm not pronouncing her name well. There is no dark energy from the beginning of the universe. It's a chicken egg problem. But vacuum can contribute to the dark energy. So from the beginning of the universe, was there no vacuum? How is it possible?
Yeah, no. Vacuum will always give energy density. If we were simply calculating energy density coming from vacuum, using quantum field theory, we get a wrong number. I told you. If simply calculate, it's 10 power 122 times larger than what we see at present. So that has to be corrected. So we realize that we are doing the wrong calculation. So what vacuum fluctuation will have to give value at most what we are observing today. At most. Because they will give you cosmological constant lambda, and vacuum fluctuations are the same, as you said completely correctly, that they will be the same whether you do it now or you do it in the early universe. Vacuum fluctuation. So that lambda will be exactly the same. So you have to constrain it to the present observed value of cosmological constant. But early universe inflation did not happen because of this vacuum fluctuation. It happened because of constant energy density, I told you. That was something different. There was some other field and it had a constant energy density. It's because of that. So vacuum can be of different kind. See how many oscillators is a vacuum. So if whenever you have a vacuum, you have to see vacuum of what. So if it's the vacuum at present you are talking about, then it's the lowest energy state of that, and you find that its energy density should be constrained by cosmological constraints at present. Okay.
Yeah. So I think that gives some. So the next question, this is Simran Patnaik. If we do not know what dark matter is, how can we say that you are mentioning humans are also dark matter? Also, what is the basis of existence of dark matter?
Yeah, sorry. Actually, I did not have time to show the picture of that. So let me just say in words that I had a whole slide on that. That you see, what happens is that you know galaxies, and you can see how objects are moving around galaxies at far away distances. So can I just take 1 minute to show one slide, Devkan?
Yeah, please, please.
Okay, maybe that it will be because just wait. Yeah, here it is. So you see, the galaxies are luminous. So let's take yellow part as a galaxy, luminous galaxy, and whatever you see in the galaxy, there are objects which are moving very far away from galaxy also. So some molecular cloud or some stars. So this is a star I have marked here. Now using Kepler's laws, you can simply calculate its velocity. And you will find that, let's not go to derivation, you will find the velocity actually should go as 1/√r distance. If galaxy is here, mass, then it should go as 1/√r. So actually, if you plot the velocity versus distance curve, you should get this dashed curve. But what you find is actually the distance, if you go far away from galaxies, there's nothing in the galaxy. You see galaxy only some luminous object, and very far away there is empty space there, but velocity does not decrease. Keplerian velocity does not decrease as it should. That means there must be some mass. So this is the way the dark matter was inferred. So these kind of observations have been made very detailed for all kind of clusters, everything, and everywhere you find that Keplerian laws and all these laws are not working unless you include some matter which you don't see. That's called dark matter.
All right. So I will take this last question because our next speaker is already, we have overshot the time. This is the last question I would like to put it before you. How do we observe the cosmic strings in our dimension? The phase transition that you are telling.
Yeah, sure. Cosmic strings are in our dimension. There is no extra dimension. I think you are probably thinking about string theory, which is string theory is different. That is in higher dimensions theory. The cosmic strings are like flux tubes and vortices. They're not superstrings. So they are formed by phase transition in our universe still. So they will be in our dimension, 3 dimensions, no problem, 3 + 1 dimension. And you'll observe them, and there are various observation people have. They have gravitational effects, certain kind of gravitational effects, and using those gravitational effects by looking at star images or galaxy images, you can try to detect them. That's what people are trying to do.
Yeah, I think there are many more questions, but if anybody is really interested, you can. I would request that Professor Srivastav can reply you. Yes, I would request on my behalf, you can write a mail if you want your particular question to be answered. So I think let us thank Professor Srivastav for illuminating us on this topic, the universe and elemental particle phases. Thank you, Professor Srivastav.
Okay, sure. I'll stop presenting now.
Sir, good afternoon.
Good afternoon, Devkanta. Good afternoon.
So Babita madam is there? Sir, you can project your slides, maybe first slide.
Yes, Devakant sir, I'm here.
Yeah, okay, good.
Can you see my screen?
Not yet. Yeah, it is coming.
Is it there?
Yes, sir.
Devkanta, in case if I lose connection, you please give me a phone call because I'm not seeing myself here. Only I see the presentation. So if I'm lost in between, you just inform me.
Yeah? Yes, sir. I will do that.
Thank you.
So, Babita madam, would you like to, or I'll carry on this session?
Sir. Please
Yeah.
carry on this session.
Okay, good. So welcome everyone again to this second talk of today. So the second talk is will be given by Professor P.S. Anil Kumar from Indian Institute of Science, Bangalore. So let me give, I mean, it is my honor because to introduce him. In fact, many of you who are here, I was his first PhD student at IISc. So if I briefly tell about Professor Anil Kumar. So Professor Anil Kumar obtained a doctorate from University of Pune. Then he was a Dutch Technology Foundation postdoctoral fellow in the Netherlands. After that, he moved to Max Planck Institute, Germany, Halle, for Max Planck postdoctoral fellowship. And subsequently, he was awarded with Alexander Bonhoff Research Fellowship. And after finishing this postdoctoral fellow in the Germany, he joined Indian Institute of Science, Bangalore Physics Department in the year 2004. And his research interest mainly focuses on this magnetism, spintronics, magnetic nanomaterials, and this heterostructures, various kind of oxide heterostructure, metallic thin film heterostructures, topological insulators, and the magnetic and transport properties of ultra thin layers. And he has actually, he basically, I would tell to my knowledge, because I was at that time a PhD student, the term this spintronics was not very well known in the Indian community. So I think he was the first person to popularize the spintronics physics or the spintronics research in India. That's what at least I can tell about that. And he has many awards and accolades to his credit. There are, I will not list all. Recently, he was awarded with the Professor C.N.R. Rao Bangalore India Nanoscience Award. And he was also, he has received DI Radharaman Lecture Award. And there is a Microsoft Research Award, Outstanding Young Faculty Award. And this Narcissus Scopus Young Scientist Award. And UK India Education Research Initiative Research Award. And also he got many Young Scientist Award during his early career of his research. Besides these awards and accolades, he also has many responsible positions. He was working as the Dean of Undergraduate Program Indian Institute of Science. He also recently, he has become the Dean Administration and Finance Indian Institute of Science, Bangalore. He's also working as General Secretary, Material Research Society of India. And so he has many more other responsible positions, which I have not listed here. But one thing what I told is he's an experimentalist. His experimental skill is very good. That's what I have learned from him. And as I mentioned, so he is the first person to introduce or to popularize the spintronics in India. So today he has chosen a topic, Introduction to Spintronics. I think it is at the students level, so people will enjoy this talk. So with this brief note, I would request now Professor Anil Kumar to please deliver this talk. Thank you, sir, very much.
Thank you, Dr. Devkanda. Thank you. I thank the organizers of CET for inviting me to give this lecture to the students of CET and the students around. So I decided to talk about spintronics today. Am I audible correctly, Devkanda?
Yes, sir. Yes, sir, you are audible.
Okay, fine. So this is the Indian Institute of Science, the main building. And those who have not visited IISc, I would strongly encourage you to visit IISc and also look for higher studies at IISc. So let me just start with one slide, which gives a very, very basic introduction. So we all know that, if you take an atom, see, if you look at an atom like a cartoon, you see there's a nucleus and the electrons are orbiting around this nucleus. And also, if you really go to the quantum picture, then you will see that there's a nucleus, and then you have these different atomic orbitals like 1s, 2s, 2p orbitals. So the basic of the magnetism is coming from these electrons mainly. So the electron has got something called a spin of an electron, right? So you know that the electron can have two different spins, maybe up spin and a down spin electron. Or you can consider this as an electron with a north pole and south pole. This is just an analogy, so don't take it like that. And you can have two types. One is north pole at the bottom, and the other one is north pole at the top. And you can just say that this is upspin and this is the downspin electrons. So now these electrons, are around this nucleus as well. So that can give rise to something called an orbital angular momentum, and the spin of the electron itself giving a magnetic moment called the spin magnetic moment. So for any material, if you talk about magnetism, it is coming from both orbital angular momentum and the spin angular momentum. And today we are not going to talk about the magnetism in material. We are going to talk about a topic called spintronics. Soon I will tell you what spintronics is. So the spintronics exploits the spin of this electron, right? So now if I just tell you what spintronics means it's spin-based electronics. All of you know about electrons. The electron is a particle with a charge as well as a spin. So just now I told you that the electron has a spin, and the electron, all of you know, that has got an electric charge. And now if you talk about conventional electronics, all of you have studied diodes, transistors, etc. What you're using there is the charge of the electron. Electron's charge is used there in the conventional electronics. When you talk about a diode, when you talk about a transistor, you talk about IV characteristics and everything. So this is all based on the charge of the electron. But the electron has got another degree of freedom. This is the spin of the electron. And we start using the spin of the electrons along with this charge, then it is called spin-based electronics. If the electron didn't have a spin, then there's no spintronics. So what we are using here is making use of the spin of the electrons along with this charge. So that is why this area is called spin-based electronics, or the short form people call it as spintronics. In the late 90s, when this area was developing, initially people gave the name magnetoelectronics, but that was not very popular. The name is not very fashionable. You also need to have fashionable names. And then this word spintronics was coined in the second half after 1995 to 2000 time scale. And this becomes a very interesting topic. And you all know that Department of Electronics is there in many places. Now I won't be surprised after some time, if there is emphasis on a subject like spintronics comes up, because the kind of application that you will hear about spintronics is enormous. That's why it's a fast developing area. So usually in a regular lecture, I ask the question at this point of time, how many of you are using spintronics? So usually the response I get is that, unfortunately, I'm not able to see you personally and then talk. Usually I get the response that, majority of the students won't raise their hand thinking that they're not using spintronics. Then I ask the question, I'll rephrase the question, how many of you are using a computer? Then I'll ask the question, how many of you are using a computer after 1998? So then almost everybody from the audience will raise their hand saying that they are using a computer after 1998. So then the good news is that if you are using a computer that is made after 1998, all of you are using spintronics. So that is the idea of this lecture, where we are using spintronics and how we are using spintronics, what is the future of spintronics. That's what I will cover in this lecture. So if you look at the spintronics technology, so this is the spintronics materials technology, and there are people who are contributing to the spintronics material technology are here. You need electrical engineers, you need computer engineers, you need electronics engineers, you need physicists, you need chemists, you need material scientists. All these people will come and contribute to the spintronics material technology. And what is coming out is amazing things. One is speed, location, angle sensor, right? Spintronics allows you to make sensors which are very, very sensitive, in the sense that suppose if I have a magnetic field sensor here, and if I have a magnet here, the quality of this magnetic field sensor is decided by the fact that if I take this magnet away from this magnetic field sensor, still the sensor senses this magnetic field. Second thing is that I make this magnet smaller and smaller and smaller, and still at large distances, if this sensor can sense this magnetic field, it's a very good sensor. So the spintronics technology will allow you to develop, very high quality magnetic field sensors. Now you may ask the question, if I have a magnetic field sensor, where should I use it? Or where can I use the magnetic field sensor? I would say that, imagine that, you are bicycling and you keep this magnetic field sensor on the rim of your bicycle, and then this tiny magnet on the tire. So, no, sorry, this is on the fork and this is on the tire, and you are cycling. So then what happens, as this tire rotates, this magnet comes in front of this magnetic field sensor, it gives a signal. And again, in the next revolution, again you are moving forward, and then this comes back again in front of this magnetic field sensor, it gives the next signal. The total distance traveled is 2 pi r. The time taken between two signals is delta t. So 2 pi by delta t gives you the speed of your bicycle. Imagine a clean way of looking at the speed of your bicycle. There is no cables, and those who are riding bikes will understand when the cable breaks, speedometer cable breaks, it's not very convenient. So imagine this is a contactless speed sensor. So this is one of the interesting things. Now imagine that I have a door and I wanted to open that door. So you can open the door like that, or I can keep a motor on top of this door and I can switch on the motor. The motor opens, the motor rotates, and the door opens. So suppose, imagine that this is the wall and this is the door, and you switch on the motor, the door opens and it comes close to the wall. Now, if I don't switch off this the motor in time, this door will come and bang onto this wall. So what I will do, I'll keep a tiny magnetic field sensor here and a magnet here. And when this door opens, when it comes very close to this magnetic field sensor, there is a signal, and the signal is fed back to the motor saying that stop. So this door opens and just stops like that. So it has become a position sensor. Now imagine that on this travel, if I'm taking magnets at regular intervals, for every 10 degrees you get a signal. So you know that what is the angle, right? So similarly, there are hundreds of such applications. If you take a modern car, you will see more than 30 magnetic field sensors for different purposes, right? Fuel injection, acceleration, so many things. So I just wanted to tell you that your imagination is the limit where you can use a good quality magnetic field sensor. So the spintronics technology will allow you to get good quality magnetic field sensors. That's one of the applications. Second thing is that it is heavily used in data storage. So that's why I asked the question, how many of you are using a computer which is made after 1998? So the computers which is made after 1998 and which employs this magnetism to store the information is using spintronic technology. So where are we using this spintronic technology, for which we need to understand how information is stored in our computer. So imagine, let us now examine how information is stored in our computer, right? So, okay, one more thing, I will be going immediately after that, another, if time permits, something called magnetic random access memory, and I will not go to the next generation spintronic devices like, spin field effect transistors, spin memory, quantum computing. There are a lot of things which are for the future. So let us don't worry about it right now. So let us understand what is the basics of spintronics. And I'm going to talk about now data storage. So how information is stored in your computer hard disk. Imagine that this is a magnet. So this magnet, this cap is the North Pole. Assume that this is the North Pole and this is the South Pole. So I have a magnet with a North Pole and a South Pole. I'm using a cap just for my convenience to show you that this is the North Pole. So now if I keep this magnet on my palm with North Pole facing towards you, when I face the North Pole towards you, so let me adjust, yeah. When I face the North Pole towards you, I say that this is a zero state of this magnet. Then what can you do? I can take this magnet and put it towards me. The North Pole is towards me. I can say this is a one state. So with one magnet, I can define a one state and a zero state, right? So now if I have two such magnets, and when I have both the North Poles towards you, it is a zero state. Now if I keep this North Pole towards me, it has become 1 0 state. If I kept this North Pole also towards me, it has become one state. Now with the two magnets, what I have created is 2 bits of information, right? So this one magnet represents 1 bit. So you know, in the computer hard disk, you store information in terms of zeros and 1. So it's a 0 state and a 1 state. Now with the 2 bits, I mean 2 magnets, I have 2 bits. Now I have third magnet, 3 bits. So if I have 3 bits like this, now it is 0, 0, 0, and it has become 1, 0, 0. It has become 1, 1, 0. Now if I turn this thing also, it has become 1, 1, 1. So with the 3 magnets, 3 bits of information. This is precisely how you store information in your computer hard disk. So now, when you talk about a magnet, right? So I'll come back to that. Yeah. So now, if I have 4 such magnets, I can create 4 bits of information. So it's a 0 state, 0 state, 1 state, 1 state. Like that, you store information in your computer hard disk. Now, in order to store information, like usually you have 8 bits forming 1 byte. So what's happening in your computer hard disk? So forget about what you type and how it is converted and then how the information goes to the magnet. You just don't worry about it. But when the magnets are in this configuration, like 0, 1, 0, 0, 0, 0, 0, 1, it represents the alphabet capital A. And if it is 0, 1, 0, 0, 0, 0, 1, 0, it represents the alphabet capital B. Like that, for every alphabet, capital, small, numerics, everything, there is a unique combinations of this magnet orientation. So once you have these magnets oriented in the right direction, you have stored that information there. So now you may wonder, right? If you have such magnets, you know how many magnets are there in a 1 TB computer, 1 TB hard drive? It is 1 into 8, because 1 terabyte means you have to multiply by 8. 1 into 8 into 10 power 12. So almost like 10 power 13 magnets. Imagine how many magnets, 10 to the power 13 magnets are in your computer hard disk. If I use these magnets, so 2 things, very important. If I bring these 2 magnets close to each other, what happens to this magnet? If all of you know that if I bring 2 magnets like this, they will repel. If I bring 2 magnets like this, they will attract. So if I bring 2 magnets like this, what happens? Beyond a certain distance, this flips. So if you have worked with magnets, if you take 2 bar magnets and bring them close, you will see that immediately it flips and goes like that. So what happens? If I write information like 0 here, I should keep the next magnet at a faraway distance, so that the presence of that magnet should not switch its magnetization. So if it switches the magnetization, it will become 10, 10, 10, 10 like that. So we don't want that. So we keep them at faraway distance, so that the presence of one magnet is not influencing the second magnet. So now imagine, first of all, you need to make these magnets far away, and also you need to store 10 power 13 magnets. Maybe if I'm sitting in this room, maybe if I have, this room can take maybe 200 such magnets. Imagine if I wanted to have 10 power 13 such magnets, you may need your entire Odisha state to store this information. But you know that this information is stored in a small hard disk. So what is happening there? So what is happening there is that now you look at here in this curve, don't look at this graph. In this graph, so this is something called magnetic force microscopy image. The magnetic force microscopy image will image the magnetic domains. So that means if the magnet is magnetized towards you or towards me, I can find out from here. So imagine each of this bit now is having a width of 45 nanometer. Imagine this is the image from a hard disk of 2000, where the density is 35 gigabit per inch square. You see the width of the magnet is 45 nanometer and the length is 380 nanometer. So now you understand, how you can jam pack large number of magnets. So 45 nanometer, how small is 45 nanometer? 45 nanometer means if I take my hair, typical diameter of hair is 50 to 100 micron. If I take my hair is say 90 micrometer, I take my hair, vertically split 2000 times. That one piece of that is 45 nanometer. Imagine that means in my hair space, I can have 2000 such magnets of this size. Then you understand why we are able to put large number of magnets there, right? So this is how we make the magnet smaller and smaller and smaller. And then you read the information and write the information. Now, if you look at this graph alone, this curve alone, you see that when you, in 1980s, the size of the bit was, 10 micron or more. As time progresses, you see the bit size becomes smaller and smaller and smaller. It was going in that trend, it would have continued like that. But you see, suddenly in 1998, it changed its slope. And suddenly the size of the bit became smaller and smaller and smaller. When the size becomes smaller, you have larger storing capacity. So this flip happened around 1998. So I asked you the question, who all are using a computer which is made after 1998? This should be read along with this change in slope. That means that is the point at which spintronics technology got introduced into our computer hard disk, and because of that, the size of the bit, we could reduce the size of the bit drastically and consequently increase the storage density of your computer hard disks. Now, let us understand certain things. Now, I keep this magnet like this, which is with the north pole towards you, is a 0 state. When I want to convert it into a 1 state, I picked up and put it like that. But in your computer hard disk, when you have 10 power 13 such magnets, you will not be able to go and pick up like this and put it like this, or pick up like this and put it like this. So there should be a mechanism of changing the magnetization. So there comes this particular picture. Now, if I take a ferromagnetic material in a magnetic field, imagine that I'm considering a single crystal ferromagnet for the time being. And for any ferromagnetic material, single crystalline material, I can define something called an easy axis of magnetization and a hard axis of magnetization. It's very easy to understand. Easy axis of magnetization, the word suggests it is easy to magnetize a material along that direction. Hard axis of magnetization means it's hard to magnetize a material in that direction. So now you must have seen hysteresis loops. You have studied in the 12th standard textbook. Look at here. If I take so the one which you are familiar with is a collection of magnetic particles where easy axis, hard axis, everything is combined together. That's why you get a hysteresis loop, something looking like this. Now, what is happening here is that I'm taking a single crystal ferromagnet and I'm applying a magnetic field in this direction. So here what happens, if I apply a magnetic field, everything gets magnetized in your direction. And now if I reduce this magnetic field back to 0, again it is fully magnetized in that direction. So this is the easy axis of magnetization, and I apply a magnetic field. So all magnetic moments are aligned in the direction of the applied field. Even if I remove this magnetic field, it remains there. So that means this material which is magnetized towards you will remain magnetized towards you even if there is no applied magnetic field. Now, but if I change the direction of the magnetic field to the negative direction, and if I start increasing this magnetic field, above a particular field, the magnetization reverses. That means it goes to this direction. And now I've reversed the magnetization, so your 1 state has become 0 state. Now, if I come back again, back to 0, nothing happens. If I come to this field, and then what happens? If I apply a slightly larger field, it switches to your direction. So this field at which it switches called the coercive field. So this aspect is used for the memory concept in our computer hard disk. So this is a 1 state, this is a 0 state. Now the trick is that you switch the magnetization from one direction to the other direction. It is possible you take your computer hard disk to a magnetic field, but the problem is that everything will switch. You don't want that. You want selectively one bit to switch. So what you will do, you all have done this experiment. If you take a screwdriver, you wind a wire around it and connect a battery to it, immediately you see magnetism developed there. If you reverse the battery direction, it gets in the opposite direction, right? So similarly, we will be using some local magnetic moment, magnetic field creation, which is my next transparency. There you apply a very local magnetic field and apply a local field to switch it in this direction or that direction, so that the neighboring bits are not getting affected. So you can selectively switch the magnetization. Now comes the second issue. How do you know that it's a 0 state or a 1 state? Here there's a cap. So your job is simplified. When you see the cap towards you, you can say, oh, it's a 0 state. When it is towards me, it's a 1 state. But in a computer hard disk, magnets do not have any caps. You have to understand in which direction it is magnetized. Here comes, say, suppose if I give you a magnet and ask you to find out which is the North Pole and which is the South Pole, you'll be doing different experiments. One experiment is that if you have another magnet where North Pole is marked, you bring that magnet and find out whether it's attracting or repelling. Depending upon that, you can say it's the North Pole or South Pole. Or you can hang it, in a thread. So this magnet will get aligned in the north-south direction. The third one is that you bring a compass. When you bring a compass, the compass will look at it. Oh yes, it is magnetized towards you or towards me. But now, if I bring a compass to this, 10 power 13 magnets, the compass will see, millions of magnets together. So then, the compass will be confused. So now the job is to make a compass which can sense magnetic field from a single magnet. A single magnet means if I take a magnet, there are magnetic lines of force outside. So if you can measure these magnetic lines of force, or if you know the direction of these magnetic lines of force, then you know that whether it is magnetized towards you or towards me. So here comes a magnetic field sensor. If I bring a magnetic field sensor, prior to 1998, people used a material called permalloy. The permalloy is an alloy between nickel and iron, 81% nickel and 19% iron. This material has a property called magnetoresistance. That means when you apply a magnetic field, the resistance of the material changes. It's called magnetoresistance. So if there is one oyster of magnetic field outside here, and if I bring permalloy on top of it, if you measure the resistance of permalloy, the permalloy resistance changes by 2-3%. So that means if it was 100 ohm material, and if I bring on top of this magnetic field, it changes to 97 ohms or 98 ohms. So that means it's a 2 to 3% change in the resistance. So this resistance change is used to understand whether it is magnetized towards you or magnetized towards me. So, and now if I make this magnet smaller, half the size of this, then the magnetic field is also less, then the change in resistance will be less. And as I keep on reducing the size of this magnet, the change in resistance becomes smaller and smaller. As you know, as a physicist, for any measurement, there is a noise. So finally, the change in resistance becomes comparable to the noise in the system, so that you are unable to find out whether it is magnetized towards you or magnetized towards me. That is why the slope of the curve, which I showed you earlier, was very slow. Because you make the magnet smaller, the magnetic field is less, the sensor is unable to pick up the signal. So you have to improve the sensor continuously. So the improvement of the sensor continuously was changing the size smaller and smaller and smaller. But in 1998, we introduced, a new concept is introduced, which is a spintronic device called the giant magnetoresistance. So I will talk about giant magnetoresistance as well. The name itself suggests the resistance of a material changes very, very drastically. So even with a very small magnetic field, you see large change in the resistance, which is measurable, so that you can make the bits even smaller, so that still change in resistance can be measured, right? So now if you look at a computer hard drive, so look at a computer hard drive here. So here, the magnetic moment of this magnet is lying in the plane. So as time progressed, what happened was the technology improved, like in real estate. If you go to a village, you see big palatial houses. But if you come to the city, you will see it's a vertical flat. So the real estate in the computer hard drive is also very expensive. So people thought that from the in-plane magnetized system to perpendicular magnetic systems. That means you can have now North Pole upward or North Pole downward. So it is one state and it's a 0 state. So like that also you can store the information. So let us look at a modern computer hard drive. where the north-south pole is like up or down. And this is a yoke. Look at the yoke here. And this yoke has got a winding of wire winding around it. Now, if I pass current through this wire, so the current passes through this, and when current passes through this thing, it generates a magnetic field, and you see that this yoke is getting magnetized. And look at here, this yoke width is very, very small. So that means the magnetic field generated here is much higher, and on the other side it is much wider, so that this is for the flux closure. So now here the magnetic field is applied. You increase the current such a way that the applied magnetic field is higher than the coercivity of this material, so that the single element would be reversed in that direction. So you pass plus current, it gets magnetized downward. You pass negative current, it gets magnetized upward. So that means when you want to write some information, imagine that you wanted to write, in the computer hard drive, there are several tracks and the bits are written in each track. So when you try to write something, you hear a sound. So what is that sound? There is a hard disk which is rotating at 10,000 RPM speed on top of this write head. And then what happens? Each bit is brought below this write head, and you apply a magnetic field, make it 0 or 1, bring the next one, apply magnetic field, make it 0 or 1, bring the next one, like that you write the information. So that is why when you try to write the information, you hear a sound, because something is rotating at a speed of 10,000 RPM inside your computer, and you bring each bit, and also you have a registry, this nth track, nth bit is this information. So like that, you store information in your computer hard disk, and you can switch the magnetization locally to store the information. Now comes the most important aspect, is a read head. The read head is the one that measures the direction of this magnetic field and tells you whether it is a 1 state or a 0 state. Similarly, when you try to read information, again, this hard disk rotates at a large speed, and each bit is brought below this read head, and the information is read as 1 0 1 0 0 0 1, like that. And then your computer system will interpret that into all this processing, and then something will appear on your screen, okay, alphabets or whatever it is. So let us don't worry about that processing thing. Let us understand the fundamentals. And the fundamental is that the information is stored in a computer hard disk in terms of tiny magnets. And this read head is the hero here. So this is made up of giant magnetoresistive material, GMR. So if you look at this graph, you see it was going at a very slow speed, and suddenly in 1998, it started increasing drastically, right? And now you see over a period of time, it is becoming slowed down. So now growth is a bit slow. So now all these things, what is the consequence of all these things? If you consider one of the early IBM computers, it was sitting in a big hall, and the density was 2 kilobyte per inch square, and the speed was 70 kilobyte per second, and the information of 5 megabyte was stored in a 24-inch hard disk, 50 of them. Imagine 50 hard disks of 24-inch diameter was used to store information 5 megabyte. Now you know that density has become almost like terabit per inch square, and with a 2.5-inch hard disk, you can now store TBs, terabytes. So this is the progress that has happened, and the real, one of the major, achievement is the read head, which is giant magnetoresistors. You may ask a question: will this continue forever? Will I get a 20 TB computer or a 100 TB computer or a 1000 TB computer as time progresses? With the current technology, there are some limitations. For example, any ferromagnetic material, if you make them smaller and smaller and smaller, it reaches something called a superparamagnetic limit. So below that value, it loses its ferromagnetic nature. Superparamagnetic means at any instant, if you look at it, it is magnetized in one direction. If you look at it again, magnetized. So it keep on fluctuating, because the energy barrier to go from this side to that side can be overcome by the temperature, say room temperature. So the barrier height is smaller than the room temperature. That's why it keeps on fluctuating and you can't store information, right? So that's why alternatives are being made. And again, now, as I told you, perpendicular magnetic recording with the pattern media, now people are making it smaller and smaller and smaller, and you can get 4 nanometer kind of bit size. So 4 nanometer means you take your hair, now vertically split 20,000 times and take one piece of it. That's how the technology is developing. Yeah. So now let us understand, since we have learned about all these things, let us understand what is giant magnetoresistance. So this giant magnetoresistance is, there are 2 groups. One is a group of Professor Albert Fert, and another group is by Peter Grunberg. Professor Peter Grunberg from Germany and Professor Albert Fert from France. They were working on this something called giant magnetoresistance. In the sense, they had the idea in 1970s. So they were trying to make multi-layer films. Like, what they did was they took 30 angstroms of iron and 9 angstroms of chromium, and then they made a multi-layer stack of say 50 such layers or something like that. So if you take a pure iron film and if you measure the magnetoresistance, extremely feeble, nothing. If you take chromium and measure the magnetoresistance, very, very feeble. But they had the genius to think that let us make this multi-layer of iron, chromium, iron, chromium, iron, chromium like that, 50 by layers. And then, for example, this work is from Professor Peter Grunberg. This is from Professor Albert Fert's group. They found that if you look at the resistance, now the resistance changes by almost 50%. Imagine for permalloy, it was 2 to 3% change in resistance. Now you see, this particular combination gives you 50% change in resistance. When 50% change in resistance, you can make your bit even smaller and then, still sense the magnetic field. So this is the birth of, the giant magnetoresistance. After several years of hard work, they were successful in getting this giant magnetoresistance. And this was further taken up by Professor Stuart Parkin, and he has developed, he made a lot of improvements in this kind of systems, and that work has led to the introduction of this giant magnetoresistance in our computer hard drives. And this giant magnetoresistance, which is introduced in the computer hard drive, fetched them. See the genius, in 1970s, they conceived the idea because the growth of thin films were not that, prominent at that time. So they worked. In 1987-88 time scale, they showed that it is possible to have giant magnetoresistance. In 1998, it came to our computer hard drive. In 2007, they shared the Nobel Prize in Physics. This is how dedicated people work. So now let us understand, right, why this giant magnetoresistance is coming. So many of the engineering students may not know about the band structure. Still, let me just tell you that there is a way in which electrons are filled in a material. In the sense that, we call it as a band structure. So how many electrons with the what energy, with the what momentum can be present in a material, etc. So this distribution is given by this band structure. If you consider a paramagnetic material, at the Fermi level, there will be equal number of upspins and equal number of downspins. But if you consider a ferromagnet, which is a half metallic ferromagnet, you will see that for one spin, this is a conductor. For the other spin, it is an insulator. So this is called half metallic ferromagnet. But if you consider the conventional ferromagnet, there is an imbalance between the total number of upspin electrons and total number of downspin electrons, and that is given by spin polarization. So this has got 0 spin polarization, and this has got 100% spin polarization, and materials like iron, cobalt, nickel has got something around 30-35% spin polarization. So the spin polarization of this material is the one that is responsible for all this phenomena. So what's happening? If you consider a normal metal, and if you pass, both upspin and downspin electron, you see that after passing through this metallic layer, the number of electrons coming out on the other side will be equal number of upspin and equal number of downspin electrons. That means through a copper wire, if you pass current, 50% upspin electrons, 50% downspin electron. When it comes to the other side also, it will be 50% upspin electrons and 50% downspin electrons. But if you consider a ferromagnetic metal, what happens? If you pass 50% upspins and 50% downspins, by the time it comes to the other end, you will see that the scattering for one type of spins are more compared to the other spins, and so that there will be a net spin imbalance when it comes to the other side. So this scattering is due to the band structure, spin-dependent band structure, which we'll not worry about here. So the take-home message is that if I pass electrical current through a normal copper wire, 50% upspin electron, 50% downspin electron I pass, and finally it gives you 50% up and 50% down. But if I pass through a ferromagnetic material, depending upon the polarizations, spin polarization of the material, the number of upspin electrons will be different than the number of downspin electrons. Now, what they did was they made a combination of these two. So what they did, they made two ferromagnetic layers, and there's a non-ferromagnetic metallic layer in between. So now you see, when I make these two ferromagnetic layers parallel, what happens if I pass 50% upspin electrons, 50% downspin electrons here, you see that the number of upspin electrons which is coming here is more compared to the number of downspin electrons. So more electrons come here, but large, predominantly upspin electron and some downspin electrons as well. Now the trick what I'm going to do, I'm going to switch the magnetization. Now these two ferromagnetic layers are magnetized in one direction. I'm going to make them opposite to each other. So if I make them opposite to each other, you see that this is magnetized to the right and this is magnetized to the left, and you pass equal number of upspin electrons and equal number of downspin electron, you see that this electron, this will scatter predominantly the downspin electron, this will scatter predominantly the upspin electron, and finally the total number of electrons coming out will be much smaller. In the previous case, large number of electrons came out. In this case, small number of electrons came out. When you pass current through something, and if you have more resistance, less electrons come through. Low resistance, more electrons come through. So what's happening is that by switching the magnetization of this material parallel and anti-parallel, you can decide whether you have large number of electrons coming. Large number of electrons coming out means less scattering. Less scattering means low resistance. Less number of electrons coming out means more scattering. More scattering means high resistance. So just by switching the magnetizations parallel and anti-parallel, you can reach a high resistance state or a low resistance state. So that is how the giant magnetoresistance works. So what they did was they put a certain thickness of chromium. For certain thicknesses of chromium, these two ferromagnetic layers align anti-parallelly. This is something called RKKY interaction and many things which we don't have to worry. So they are anti-parallel. Now if I apply a magnetic field, I can make them parallel. And when I don't apply a magnetic field, they are anti-parallel, then less number of electrons come out. I apply a magnetic field and they make them parallel, more number of electrons coming out, the resistance is lowered. So this is how the giant magnetoresistance works. But here, in order to break this coupling, you need large magnetic field. That is why their work needed 2 Tesla, 20 kilogauss magnetic field to switch this magnetization. So then, newer concept came up, which is called a spin valve effect, where you have 2 different ferromagnetic layers separated by a metallic spacer layer. So here what happens, if I make 2 ferromagnetic layers parallel to each other, you see to both types of electrons. One type of electron will pass through without much scattering, whereas the other kind of electron is getting scattered here, and finally it is getting scattered there, and finally this is rough numbers, if I put 100 electrons here, only 50 electrons come out. Now if I make these 2 ferromagnetic layers anti-parallel, then what happens? This spin and this magnetization is not compatible, so it will scatter, and if this electron passes through this layer, but when it comes to the second layer, again it scatters. So when they are anti-parallel, more scattering means high resistance. When they are parallel, less scattering, low resistance. But here the advantage is that they are not intrinsically coupled. They are decoupled, so that permalloy, which has got a low coercivity, and cobalt, which has got high coercivity, you can make them parallel or anti-parallel by applying small magnetic field. If you look at the magnetization here, just by applying one, see at this point, both the ferromagnetic layers are parallel. And if I reduce the magnetic field, I go to the negative side, then they become anti-parallel, the magnetization drops. And if I increase further, the second layer of cobalt also switches and it becomes parallel. So this anti-parallel state is the low resistance state, high resistance state, and this state is the parallel state, which is a low resistance. If you just want to visualize this experiment, imagine you do an optics experiment, you have a polarizer and an analyzer. If you pass light through this, there's a polarizer, analyzer. When the major axis of the axis of the polarizer and analyzer are aligned, then light passes through. Now, if I rotate this polarization by 90 degrees, then it is cross polarized, no light comes through. So now this is a valve for light. Parallel, light comes out, perpendicular, no light comes out. So it's a valve for light. Here we have a valve for spins of electrons. When the magnetizations are parallel, electrons are coming out. When the magnetizations are anti-parallel, electrons are not coming out. So this is almost like a valve for electron spin. So that's why, this spintronics, because if the electron didn't have spins, then there's no spintronics here, right? So this is how your computer hard disk reader works. So, okay, I'll just skip that. So let me just introduce in last 5 minutes one more topic, which is called tunnel magnetoresistance, right? Tunnel magnetoresistance means, in the earlier case, I had two ferromagnetic layers and a metallic non-ferromagnetic layer in between. Now I have two ferromagnetic layers in between and insulating. So here what happens, those who have studied quantum mechanics, or you will study quantum mechanics later, where you see that I have a potential barrier here. So because there is an insulating layer. So because of a potential barrier, now if an electron has to go from this side to that side, I apply a voltage across these two. And if the width of the barrier is very small, then electrons can tunnel from this side to that side. Now, not only the electron can tunnel, the electron also senses, if there are two ferromagnetic layers, ferromagnetic layer 1 and ferromagnetic layer 2, the electron tunneling also depends upon whether the magnetizations are parallel or anti-parallel, right? So this is how the tunnel magnetoresistance works. And again, I will stop here and ask a question. How many of you are using tunnel magnetoresistance? And majority of you will raise your hand saying that you're not using tunnel magnetoresistance. Then usually I rephrase this question once again, like I rephrased the first question. How many of you are using a computer which is made after 2005? Then majority of you will raise your hand. Then I will say that the good news is that you are using tunnel magnetoresistance as well. So the computer hard disks which are made after 2005, most of them have tunnel magnetoresistance there. So what is happening here? As I told you, when the two ferromagnetic layers are parallel, more electrons tunnel. When the ferromagnetic layers are anti-parallel, less electrons tunnel. So you apply a potential between these two. So when more electrons tunnel, means you get more current. For the given voltage difference, if you get more current, means you have low resistance state. When you make it anti-parallel, less tunneling. Less tunneling means high resistance, right? So you can make it parallel, low resistance, anti-parallel, high resistance. Now, if you look at the tunnel magnetoresistance, now we are getting more than 500% tunnel magnetoresistance. Imagine the GMR which we talked about was 50% magnetoresistance. Now we are talking 500% magnetoresistance. It is called tunnel magnetoresistance. Magnetoresistance for the fact that you switch the magnetization and change the resistance. Now the electrons are tunneling. See, for example, if I'm walking towards this wall, I will be stopped here. I cannot go. Whereas you have seen this movie where a man is running and he pierces through the wall and going to the other side and still running, right? So electrons can do this provided the tunnel barrier is very small. Look at here, the tunnel current. If the thickness is very high, there won't be any electron tunneling. If the thickness of this barrier is small, below 2 nanometer, then you see electrons tunnel through this barrier to the other side, right? So this is the concept of tunnel magnetoresistance, and almost same concept as the previous one, so I'll not spend time here because I just wanted to discuss something more here. Look at here in this graph once again. This is the time at which the first GMR head got introduced. This is the time at which the first MR head, which is a permalloy, got introduced, and then first GMR head. Then I told you that perpendicular recording started, and then around 2005, 6, 7 time scale, the TMR got introduced. That's why we have terabit computers today. So this is just to tell you about tunneling. Those who know about it, just I wanted to connect. When we teach quantum mechanics, we teach about one-dimensional potential barrier problem. It is exactly a one-dimensional potential barrier problem here. So the electrons coming here, tunnels through this barrier, come to the other side. And now this tunneling is more when the magnetizations are parallel, and tunneling is less when the magnetizations are anti-parallel. So let me just tell you that this magnetic magnetoresistance also can be used to store information. Here, as I told you, when the magnetizations are parallel, it's a low resistance state. When the magnetizations are anti-parallel, it's a high resistance state. Now, suppose if I have a stack like this, just by measuring the resistance, I can define a 0 state and a 1 state. Now, if I keep such tunnel junctions as a distributed, on a wire like this, then if I have a copper wire here and I keep tunnel junctions like this, and if I connect a copper wire from the top, then what happens? If I measure the resistance between this point and this point, I'm measuring the resistance of this stack. If I measure the resistance between this point and this point, I'm measuring the resistance of this stack. Now, the point is that if I have an array of this, and if I look at the ith row, jth column, if I measure the resistance, that will tell me whether it's a 0 state or 1 state. In our computer hard disk, the disk should rotate, and each bit should come below the write head or a read head for this. Whereas now, sitting at here, ith row, jth column, I know what is the resistance. Then I know it's a 0 state or 1 state. So this can be used for random access memory. Means reading can be done in nanoseconds. So in the previous case, it takes time because some disk has to rotate. Whereas the RAM which you have in your computer is much faster, right? So now you are going to make magnetic random access memory. And how the information is written here, you pass current through this top wire that generates a magnetic field. And you pass current through bottom layer that generates a magnetic field. If I pass all the currents through this line, then everybody in this line will get switched. Whereas when you apply a current through this, if you apply a current through a conductor, it generates a magnetic field. And you have another conductor that also generates a magnetic field. At the intercept, the total magnetic field is more so that it can switch the magnetization. What you want to do, you want to switch the magnetization from 0 and 1, 0 and 1 kind of thing. Just by passing current through ith row, jth column elements, I can make it 0 or 1. I reverse the current, it becomes 1. I reverse the current, it goes to 0. So sitting here, I can look at what is the state of the ith row, jth column element. I can also switch the magnetization of the ith row, jth column element. So this is why it is called random access memory, because it's extremely fast. So imagine that you have a computer instead of your 3264 GB RAM. Imagine you have a 1 TB computer which is completely RAM. How fast your computers will be. Switch on the computer, it's on, instant on computers, no booting. So what will happen in future? Your DRAM will be replaced by MRAM. And if I ask a question at this point of time, how many of you are using MRAM? Some people will raise their hand because I deceived them 2 times. But here the thing is that nobody is using right now, but it will be soon in the market. So it is called a non-volatile memory. So in our computer hard disk, things are volatile. So that means information, if it is stored, you need power backup to keep the information there. Whereas for MRAM, it is non-volatile. Write time, read time, everything is same. And in the DRAM, it is a destructive technique. So what happens in a DRAM? What happens? Imagine that this is a bottle of water, right? I can also create a memory with that. When the bottle is full, I say it's a 1 state. I remove the water out and it's empty, it's a 0 state. Now you give me 100 bottles, I can make 1s and 0s by filling water or emptying it. So actually in our DRAM also something similar to that happens. Instead of water, it is charge stored in a circuit. And when it is charged, I can say it's a one state. When it is discharged, I can say it's a zero state. Now, if it is a charged one, how do I know it is a one state or zero state? I open the bottle and pour water out. Oh, water is coming out. So that means it was full. And then again, I put it back. So that's why it's called a destructive method. And rewrite cycle equal number. And operating current, here it is much smaller operating current you need. And the standby current is also much lower. And this is what I showed you was something called a spin transfer torque based MRAM. But the new generation RAMs won't even need this much. So you're sure to replace your RAM with MRAM in future. I think with this, let me stop my talk at this point of time and let me take the questions. Hello.
Yeah, thank you, sir, very much for a nice introduction to the spintronics. So now, sir, there are a few questions.
Sure, please.
I'll be reading those questions. Probably you can answer those questions.
Yeah.
This is a question from Joy Krishna Khatei. He has written, thank you, sir, for such a nice take. I have a general question regarding future spintronics. Currently, spintronics dominate the industry of information storage and processing. But recently, a new type of electronics, that is Velitronics, has arrived. Do you think it has better future over spintronics? Is there any drawbacks of spintronics?
No, see, the thing is that every field has got its own advantages and disadvantages, right? So right now, spintronics is a technology which you are utilizing and using it. Now, many more new device concepts are coming up in spintronics itself. See, for example, racetrack memory. I'll tell you, when I started doing my PhD, when I was doing my MSc, I had a computer in the computer lab which didn't have an hard disk. I go with the floppy, put it inside, boot the computer and use it. 640 kilobyte floppy. When I started doing my PhD, I got my first computer with a hard drive, which is 20 MB hard drive. By the time I was finishing my PhD, it was 200 MB hard drive. And almost 80%, 90% is utilized. Now I'm using a 1 TB computer that's also 800 GB is already utilized. As time progresses, your requirement is also going up. So the next generation storage needs even more. The data storage is a very, very demanding area. And I was told that some data center was started in Antarctica because for this data storage, a large amount of power is gone for cooling. Whereas if you go to Antarctica, you can save that. So the next generation spintronics is what you want is faster and faster devices, larger and larger capacity, and lower energy consumption. So in that respect, I would say that spintronics is still have to go a long way. There are a lot of potential available in spintronics in future. I just told only about this part. I've not spoken about the concept of spin FET and quantum computing based on spins, etc. So these are the next generation spintronics. And today I was talking about ferromagnetic materials applying magnetic field. The next generation is that ferromagnetic materials, magnetization reverses with electrical current. Now you don't need even magnetic materials with a high spin orbit interaction, you can use it. So please understand, spintronics has a lot of potential ahead. Valitronics is another area which is emerging. Yeah.
Okay, I think that clarifies that question. So there is another question. This is Soumya Sarthak Nayak. What are the applications of spintronics in medical field?
Yeah, see, wherever you need good quality magnetic field sensors, there's a lot of work which is going on in the medical field also for magnetic field detection. Plenty of work, wherever magnetic field sensor is needed. Nowadays, magnetic field sensor is needed everywhere. So people are also working towards achieving, sensitivity of, SQUID with this magnetic field sensors. SQUID means MRI machines and all those kind of things are working with, that principle where you need to cool everything. Every hospital needs liquid helium to cool their, MRI. So suppose if you can develop this thing at room temperature with the spintronics, I would say that, future, you don't have to be subjected to very high magnetic fields and this expenditure on, MRI imaging, everything will come substantially down. A lot of potential, lot of potential.
Okay, so there is a next question from Suraj Ranjan Shahu. He has asked, sir, in our modern PCs, we are using SSDs. I don't know what is SSDs as storage. Those are using 3D technology currently. Can you please explain how tunneling phenomena is occurring in these SSDs?
No, I think SSD is a complete the solid state device. If, for example, if you have a MacBook that is based on solid state memory technology. So SSDs nowadays you've got combination of SSD plus magnetic stuff. So SSD is slightly more faster than magnetic memories because there again this information, but it is not as fast as RAM, but it is somewhere in between RAM and hard drive. So things would be, I mean, like a magnetic disk, things would be faster. So there, I don't think that, I mean, my information is that we may not be using tunneling there. I'm not sure about it, but my understanding is that you don't need tunneling there. Yeah.
All right. I think that is the question. So I think the last question I will ask you. So
Yes,
with
sir.
that we'll end. I will give it to the convener. So you mentioned after this magnetic field change, now you told there is a electric field. Using electric field will be changing the magnetization.
Yeah.
But I hear these days people are doing this using light. They would like to change the magnetization. So how far that is from a real application?
That's also a very, very mature field right now. So people are using femtosecond and picosecond pulses to switch the magnetization. There's a lot of work which is going on. So this is called optical switching. Yeah, magnetization reversal by optics. So that's also matured and a lot of demonstration has happened. People are also showing that how it is getting reversed, etc. Yeah.
But is it coming to use in the market based on that technology?
That part I'm not sure whether it is come to the market for usage. That I'm not sure, Devkanda.
Okay, so I think with that we'll thank Professor Anil Kumar very much for illuminating on this area. This on introduction to spintronics. Thank you, sir, very much for your nice talk. Now I will hand over to the convener, Professor Ojha.
Thank you, sir, for your nice explanation. Talk was very, very interesting for me and also for all participants, I feel. And for that, I want to invite you again for another talk in coming webinar that will arrange. And this is end of the session, today's session. And tomorrow we'll start the session at 11. Thank you all.
Thank you. Thank you. Thank you for the attention. Thank you for the invitation.
Really, your talk was very, very interesting.
I'm trying to come out of the